cipher, and you can control the behavior of this chip with firmware. So there are special instructions. There's special instruction in processor. This is not a standard 83. This is not a standard like a MIPS or an Intel or whatever. It's a completely dedicated instruction set just for the baseband processor of this card. And this controls the DECT standard cipher. And what is written here is our standard operating procedure for the cipher. So somewhere in memory, you have 16 bytes of memory, and there you put your key for the cipher and the initialization vector of your cipher. And with this command, you enable key loading for the baseband processor here, which starts loading the key from this memory address. And then it waits 16 clocks, so it loads 1 byte of key or IV per clock cycle. So you need to wait the 16 clocks. This command here is like writing down 16 times a NOP command, no operation, just wait 1 clock cycle. And after that you disable key loading again. And after that you have to produce 40 rounds of, you have to do 40 pre-ciphering rounds, which just means that you start the cipher and the cipher runs for 40 rounds. And you just put the output away. You don't use the output. The first 40 bits of output are not used by the cipher, and these rounds are called blank rounds. So
we'll come back to the blank rounds later. This turns out to be a big vulnerability. The number 40 is pretty much random. They could have chosen any number here, and 40 turns out to be much too low for this to be secure.
Yeah, and so you enable the generation of key stream here with this command. You wait for 39 clock cycles, and then you disable the generation of key stream again. You just have to wait for 39, not 40 rounds, because during the execution of that command, 1 bit of output is produced. And then the cipher is ready for usage. So after you have you did run these commands on the baseband processor, then your cipher has been correctly initialized, and you can just start using the cipher to decrypt a DECT frame or to send a DECT frame over the air. And besides that, the firmware has a very useful command, which is called write state, which allows you to dump the internal state of the cipher to memory. And this command generates an 11-byte binary large object somewhere in memory, which represents the internal state of the cipher. So this is very useful for reverse engineering the cipher, because you can just run some commands of the cipher, or you can, for example, not load 16 bytes of key, you can just load 1 byte of key, or you can skip the pre-ciphering completely, and then you can write the state of the cipher to memory and look at it from your PC.
So this level of access was extremely helpful in debugging it to the point where we could find a function that we were not supposed to know. This is a cryptographic cipher where in every clock at most 5 bits are updated. So if you can look at the cipher after every bit, you see those 5 bits being updated, usually even less, and you can pretty quickly figure out what is going on there. Of course, if we hadn't had this access, we would have opened the chip, filed it down, looked at it under a microscope, which we did anyhow because it's so much fun to verify some of these results.
So here again, Starbuck helped us a lot in looking into the chips. If you don't have these commands, you have to open the card, open the chip, and look at the wiring of the chip, and have a look at all the circuits on the chip and figure out how the cipher works. But with that, you can look into the cipher when it operates, and which is very, very useful. Usually you have the problem when you analyze a cipher, you just have input and output, and you need to figure out what has happened in between. And with this command, you can look at the cipher while it's operating. So, first thing what we needed to get the feedback polynomials for the linear feedback shift registers. This was not so difficult. We decided to load special key IV combinations in the cipher. When we started with that, we had no idea how the input of the cipher looks like. So we just knew that there are 16 bytes of memory, and this is loaded into a cipher, which is most probably somehow the key and the IV in some order. And we decided to load all possible inputs with Hamming weight 1. So we initialized the 16 bytes of memory with all bits set to 0 except 1 bit, and then loaded that into the cipher, skipped pre-ciphering completely, and then dumped the state of the cipher. And when you do that, you can write down the feedback polynomials just by hand. You just need to look at the content of the memory, and you can write that down by hand. And then you can verify that using a computer algebra system to detect very obvious mistakes you might made. The next problem was the clocking. For A51, we have a majority clocking, which means that 2 or 3 registers are clocked. And for the DECT standard cipher, we didn't exactly know how the clocking looks like. And what we did, we ran 1 round of pre-ciphering. You just have to run this instruction deprep twice on the baseband processor. Then you get 1 round of pre-ciphering. And then you can write the state, and you can check what has changed between the states. So these two instructions, deprep will modify the state a little bit, and then you can check if a register in the state has been clocked 2 or 3 times, and you can try to find out which bits affect the clocking of a register. This was already presented last year, and this gave us the clocking functions. So the clocking of every register, R1, R2, and R3 is controlled by all other registers, and it's a linear function. So they just XOR some bits of the other registers, and if the result is 1, then the register is clocked 3 times. If the result is 0, the register is clocked just 2 times. The last problem was getting the output combiner. So the state of the cipher we could write had 11 bytes, or 88 bits. And we knew that 80 bits are used for the content of the registers. 4 of these bits were used as a kind of help for the implementers of the cipher, or as a kind of control or debugging bits. And 4 of these bits were unknown, and we assumed that this would be the memory of the output combiner. And what we then did was we loaded pairs of random inputs, which only did differ in a single bit. And then we ran 1 round of pre-ciphering, and we then checked if these 4 unknown bits changed. So if you have, for example, bit number 23 in your state, and you load 2 random states which only differ in bit 23, and these 4 bits used for the output combiner don't change for a lot of these input pairs, then you can assume that bit 23 does not affect the output combiner. And then we could more or less get the output combiner as a kind of lookup table or S-box. And the output combiner doesn't seem to have a very simple structure, so it's more or less looks like a cryptographic S-box. Last thing what we did was we had to verify that what goes over the air is the same as what we see in the memory of the output combiner. and we used a modified version of Patrick McCarty's DECT stack.